So first of all, I would like to thank the organizers for the invitation and for putting so much effort into this beautiful and very interesting event. Today my talk deals with maximum entropy models for texture synthesis. So it's mainly work done by Valentin de Bortoli, who is a PhD student under the supervision of Agnès Desolneux, Bruno, Galerne, and myself. And he has also been working with Alain Durmus on some results on Monte Carlo Markov chains that I will explain in the second part. But first, let me go back briefly on the problem of texture synthesis. So a problem on which I worked for quite a long time now, maybe a bit too long, I would say. So here, the problem is to design models and algorithms that take an input a texture as input and which are able to produce as output a new image which has the same perceptual characteristic but which is not a verbatim copy of the input. So one common way to do that is to see the texture as a realization of probabilities to distribution pi. So here, the images will be defined on a discrete rectangle omega with values in R3 for color images. And so we look for a probability distribution pi on the set of images RD. And so with this stochastic framework, you can formulate texture synthesis in two steps. A first estimation step where you try to infer the probability distribution pi from one single exemplar image x0, and a synthesis step which consists in drawing a random sample of the probability distribution pi. So of course, from a statistical point of view, it's a bit delusive or even a bit absurd to infer all probability distribution from one single exemplar image x0. But here, in the case of textures, we have some assumptions that make the problem simpler. First, since we consider essentially homogeneous images, we can restrict to stationary random field. So probability distributions which are invariant under translations. Another assumption that makes the problem simpler is to restrict to parametric classes of texture models. So one way to do that is to assume that you have at your disposal a family F of statistical measurements. So from the set of images to RP, so we have P numbers to characterize one texture. And we assume that these statistics, in some sense, capture the perceptual aspect of the texture. So of course, it's in itself a difficult goal to find a minimal set of statistics that precisely reflects the human perception of texture. But in this talk, we will assume that we have one set of statistics which is fixed. And now, once you have fixed a set of statistics, you can formulate texture synthesis by saying that you look for a random field x which preserves those statistics. So there are two ways of asking that, for example, or maybe others. But for example, you can ask to preserve in expectation or almost surely on the realizations. And now, apart from those statistics, you want things to get the messier possible. So you want to make the random field the more random possible except for these statistics. And one mathematical way of imposing that is to maximize the entropy of the model. So if you maximize the entropy with those constraints, you get respectively what's sometimes called a macro-canonical model for the expectation constraint and a micro-canonical model for the almost sure constraint. So it's the terminology that comes from statistical physics, I guess, but which was recalled by Mala and Bruno in a recent paper. Okay, so now, of course, in previous works, there have been many sets of statistics that were considered for parametric texture synthesis. Let me just say that on this slide, it's not at all an exhaustive overview of texture synthesis. It's just a view of parametric texture synthesis. Okay, so I won't talk at all of non-parametric texture synthesis in this talk. And of course, there have been tremendous work on non-parametric texture synthesis with patch-based method. So first, if you want to preserve some statistic linked to the covariance or equivalently the Fourier spectrum, then you would get models which are essentially Gaussian models. So this is interesting because when you fix the covariance in a stationary framework, then you prescribe the frequency content of the output texture. Now, if you want to use the decomposition of your frequency domain, which is more compliant to our human perception, you may use wavelet statistics. So that was first done by Iger and Bergen for texture synthesis, and going up to a kind of pinnacle in the work by Portier and Simoncelli, who singled out a small set, about 700 statistics, which are sufficient to characterize a very, very large class of textures. Okay, so more recently, people have used, and in particular, Gattis and colleagues wrote a groundbreaking paper that used neural network statistics to synthesize an even larger class of textures. But of course, they used many more statistics than Portier and Simoncelli. So here, I would say that this one is quite close to the state of the art in terms of visual quality, but of course it's quite long for synthesis. And even more recently, Bruno and Mala have proposed to use statistics obtained in a scattering transform, which is a transform having kind of the same architecture than a neural network, but with convolutional kernels, which are much better understood. Okay, so now you can wonder, in all these models, how do they split between micro model and macro models? And the answer is that, except in the case of the Gaussian model with covariance statistics, most of the models lie in the microcanonical framework. And why is that? It's because for microcanonical sampling, there is a quite accessible algorithm that you can use. You start from a white noise, and you take a gradient descent to minimize a functional linked to the distance of the feature on the synthesis to the feature of the original image. So I'm not saying that this functional is easy to minimize. If you look at the work by Guillaume Tartavel, for example, you may see that such functionals may have many local minima, and there are some parameters to set. But anyway, you can consider such an algorithm, especially now when obtaining the gradient of your features costs virtually nothing more than computing your features in recent implementations. Okay, but now, if you look at macrocanonical synthesis, there has been mainly two important works. The one by Zhu and colleagues, who introduced the frame model, and another work, more recent, by Lu and colleagues, who used first-order neural statistics in a macrocanonical framework. Okay, so I will detail those two works in the first part, but first I would like to mention already that one problem of this work is that, so one advantage is that you have an explicit form for the probability distribution, but one problem is that you try to truly sample a probability distribution, so you have to rely on MCMC stuff, which may be quite long to converge. So that's why the original method by Frame and colleagues, it might took some days to synthesize even one texture at the time. Okay, but we'll see. So one main objective of this talk is to build on the paper by Lu and colleagues, which triggered my attention at the time, and to better understand the mathematical results that lie behind it, and to enhance also the visual results that they obtained. Okay, one thing I forgot to tell is that it's an ongoing work, so suggestions, comments, questions are very welcome. Right. So why do we have to study macrocanonical models if they are so long? Well, in my opinion, there are several reasons for that. The first one is that I found it to be a strongly principled formulation of by-example texture synthesis. Okay, so if you do maximum entropy, if you use the maximum entropy principle that you can be critical of for texture synthesis, it gives an explicit form for the distribution, and then you can use a sampling algorithm and estimation algorithm, but you cannot know where you're headed for. And so afterwards, you can try to evaluate the precisions of the sampling or the estimation procedure. Next, one thing that I'm quite interested of is that there is a link with the modified Joulès conjecture. So It's written in the introduction of its paper in 1981, and it basically said that textures may be characterized by first-order statistics, but not computed directly on the pixel, but computed on nonlinear features, so nonlinear transform of the pixels. So that could be linked to terminations in the textures, blobs, etc. Okay, so of course, he spoke of first-order statistic of computed on textons, but he did not give an operative definition of what is a texton. So this is the whole mystery of it. Okay. Now, another thing is that if you sample a model which is of maximal entropy with some constraints on a certain set of statistics, what you get in the end will help you to understand what is encoded in your statistics, as this is a quite important question when you use statistics linked, for example, to neural networks. And finally, and I hope to convince you on that in the next sections, there are some interesting connections with Monte Carlo Markov chain results, on which we had very nice talks already by Georges Sanford, Pierre Chenet, and Stéphanie yesterday, and Marcelo this afternoon, I guess. Okay, so now, in the first part, I will go back on the form of the distribution that maximizes the entropy with those constraints. In the second part, I will explain how to sample and estimate such a model with a provably-convergent algorithm. And in the third part, I will show you some visual results of texture synthesis. Okay, maybe drink a little. So first of all, we define the entropy in the quite classical way. So P is, P, yeah, it's a set of probability distribution on the images. We take the entropy with respect to a reference measure mu, which in the applications in the continuous framework will be a Gaussian distribution. So J here will act as a regularizer. And then the entropy is defined with the classical formula minus in the integral of P log P, where P is the density of pi with respect to the reference measure, should it exist, or minus infinity otherwise. So of course, this is linked to the Kullback-Leibler divergence, and so it's in particular concave. So it would be quite nice to maximize the entropy, possibly with some constraints. So here, I go back on the definition on which I already told you something before. Here, in the old talk, x0 will be the exemplar texture, and f will be the set of statistics that we wish to preserve. And so again, we define a microcanonical model and a macrocanonical model as the probability distributions that maximizes the entropy on a constraint. So it's an almost sure constraint for micro model and a constraint in expectation for macro model. So of course, the constraint in expectation is looser than the almost sure constraint, right? So in general, as we'll see, we have some theorems that ensure that some macro canonical model exists with some technical hypothesis. So that's what we would call a maximum entropy principle. So there have been several of these in the literature. So no, I'm not claiming that we have the most general one. We have written one with this set of hypotheses. In some sense, in a framework, you can show that if you maximize the entropy with a constraint in expectation of the statistics, if you write the Lagrangian formulation of this problem, then you obtain Lagrange multipliers theta that are actually your parameters of your texture model. And so the explicit form of the texture model is an exponential distribution linked to the scalar product with theta and the features f of x. And you have to divide with a partition function z of theta, which is, of course, very difficult to compute in practice. It's usually intractable. Okay, so here, with these two hypotheses, so the first one in particular ensures that this exponential model is indeed well defined for all theta. We can ensure that there exists a macrocanonical model. So there exists a theta star, for which the associated probability distribution pi theta maximizes the entropy and satisfies the expectation constraint. And what is nice also in this theorem is that it's constructive, which means it builds the theta star by minimizing a functional which is convex. Yeah. Okay. So actually, once you restrict to this parametric class, you just need to find a distribution pi theta that satisfies the expectation constraint. And actually, you can do that. It's somehow equivalent to a maximum likelihood procedure. So if you write the maximum likelihood of your model, here with exponential distribution, it simplifies as this expression when you have a linear term and the log partition function. So this term can, of course, be differentiated very easily. And for the other one, with the first hypothesis of the theorem, you can differentiate under the integral sum, and you get this kind of stuff. And here, when you divide back by the z theta, you see that the second term gives the expectation of the statistics under the model pi theta. So in other words, the gradient of the log likelihood is the expected features of the model minus the observed feature of the exemplar texture. So one thing that you could already see is that if you have a critical point of the likelihood, this is associated with pi theta that satisfy the expectation constraint. Okay, so we would have to show that such a critical point exists, and for that we can go one step further and compute the Hessian matrix. So as you can see, the Hessian matrix, it's linked to the covariance of the feature in the model pi theta. And this is a non-negative matrix. So that means that minus log likelihood is actually a smooth convex function, and you can search for a minimum. So I'm not going into the last technical detail, but the second hypothesis that we've written here allows to show that this function is very coercive, and since it is convex and continuous, we can actually show that it is coercive. So it's a smooth convex function with coercivity, so it has a minimum at some point. And in the end, it's quite easy to show that for this minimum, you get a probability distribution that satisfies the expectation constraint, and besides, it maximizes the entropy over all the distributions that satisfies this constraint. Okay, so what's nice in this proof is that it tells you how to look for this theta star, right? You can try to maximize your log likelihood quite classically, and for that, you may take a gradient ascent on the log likelihood. The problem is that in the gradient, you have an expectation that you don't know to compute exactly in general. Okay, so the algorithm will read as this. You do a gradient descent, and at each step, you need a sample of pi theta x, and you will approximate your gradient with f of x minus f of x0. And you update, and fortunately, you will converge to something. But as in Gerson's talk, in general, we don't have an exact way of sampling the distribution pi theta. So we will have some bias in this step. And actually, if you want to show that this thing converges precisely, you have to control the errors that you make on sampling at each step. Okay, and in the end, we get a synthesized image x and some parameters theta star. Okay, so I will go on the mathematical detail of that in the second part. Now, first, let me give you some examples of maximum entropy models. First, if you consider some statistics which are linked to the average value of the pixel and the autocorrelation function here, then, of course, when you write the maximum entropy distribution, it reads this way. And you can see here that it is a Gaussian distribution. And the theta are actually linked to the precision matrix of your model. Right. So adjusting the theta correctly, you have a precise value for the mean and for the covariance function. Now, if instead of doing covariances on the pixel, but on some linear filtered version of the image, you would constrain these things here. So here, the kj is a bank of filter. If you do all the possible correlations which are summed spatially, and you put it in the exponential with some parameters in front of it, you still get a Gaussian distribution. Okay? So if you do first-order moments on some things like that, or second-order moments, but without nonlinearity, you always go back to Gaussian model. So you have to put some nonlinearity somewhere to get a distribution which is actually interesting. So that was done by Zhu, Wu, and Mumford in 1998. So actually, they considered several filtered versions of the image. So Fj here is a bank of filters. And they considered these statistics, which are summed spatially with indicator function. So that basically means that they compute discretized histograms of the filtered version of the original image. And the filters are like a Dirac to get back the intensity, Laplacian of Gaussian to get the quantity of blobs, for example, etc. They also put some nonlinear filters, even they use a convolution in the expression, but anyway. And with this model, they are able to synthesize texture like that. So as you may see, the image looks a bit ugly because actually their model is discrete. So it stands in a discrete framework with 8 quantized images in the experiment. And they relies on a Gibbs sampling strategy for this Markov chain. So this is very, very long to converge. And the estimation of the parameter is also very long. So that's why they proposed a kind of recursive strategy to enrich the bank of filter. And so one paper that drew my attention a few years ago is the one by Lu, Zhu, and Wu. They proposed to use, again, first-order statistics computed on a neural network. So here, the FK are the response of the image to a neural network. So I will go with the usual diagram in a few seconds. And they sum it spatially. Okay, so here, the FK of X are all the responses to one fixed layer. So the P is just the width of the layer. Okay? And what they are able to synthesize with that is those kind of images. So as you can see, there are some scales problem because they use only one layer. And actually, I think they were not so interested in texture synthesis. They were more interested in more general image synthesis. So they proposed some variation of this model. But for texture synthesis, the result that they have shown is these ones. And what was interesting in this paper is that they introduced, sorry, they did not introduce, but they proposed to use a Langevin algorithm for a distribution with those statistics. Okay, so the usual diagram, as I advertised you. So which statistics they used? They used this layer, which is a bit intriguing, not so shallow, but not so deep. And actually, it's a quite critical point of their papers. They could have used much more layers, but they do that in another paper, which is a bit strange, but because they do not use the easier way to include all the layers. That we have done in the next part. Okay, so actually for such a neural network set of statistics, we have been able to show the existence of a macrocanonical model with a Gaussian reference measure. So here, we'll apply our theorem about maximum entropy principle. So the features are obtained with the cal f of x. So here, the fj of x are the responses of the image to a pre-learned neural network. So the aj are linear operators. Yeah, Marcelo?
Sorry, are these networks learned on?
They are pre-learned. Yeah.
They are trained on lots of different textures, or they learn about just textures of vegetation, for instance?
No, the neural network is pre-learned. So it's VGG 16 for them. And for us, it will be VGG 19, but it does not really matter, I guess. But the neural network should work for virtually all textures.
Oh, okay.
Okay, it is brilliant. That's okay? Okay. So here we have some composed linear operators with a nonlinear unit, which is applied, of course, to all components. And we will assume that the nonlinear unit is actually differentiable. Okay, so it's not the classical point of view in neural network, but it will allow us to apply our theorem. And classically, the linear operators are obtained by convolutional kernel, but with matrix convolutional kernels. So the kernel will operate on all the layers at once. Okay, and now the last step is to average the features spatially. So here I is, again, a spatial index. So we compute first-order moments on several layers of the neural network. And if you put an assumption of maximum rank for the neural network, meaning that the differential has rank minus P and D, D being the number of values, of color values for the, of numerical values for the pixels, and P would be the number of statistics that you use. So if you want to do things which is not incredible, you should use less statistics than the number of pixels of your texture, right? So P should be much less than D. And if you assume that the nonlinear unit is sublinear, then we can show that the macrocanonical model exists with respect to a Gaussian reference measure. Okay, so I will not go on the proof of this result. So now we will try to sample and estimate such a macrocanonical model using sampling algorithm and estimation algorithm on which Valentin has been working with Alain Durmus, so Marcelo and Anna, who are there. So first, how to sample pi theta. So again, for our maximal entropy distribution, pi theta can be written with a density with respect to the Lebesgue measure, which writes in this way. So we have, again, theta times the features. I've put the x0 here, but it does not matter because you can absorb it into the partition function, plus the regularization. Okay? And one possible algorithm to sample such a distribution in the continuous framework is to use the discretized Langevin dynamics. So you can understand that as a gradient descent on the functional V, but with some random component added at each iteration. Okay, so since it is a discretization of a continuous stochastic differential equation, if you want to have things that are actually consistent, you should take some steps, gamma n, that goes to 0. If you want to target the proper probability distribution pi theta. If you use constant step size in this sampling algorithm, it has a stationary distribution, but it may not be pi theta. Okay, so taking gamma that goes to 0, it's actually important here. And so there has been some results on the consistence of such a Markov random chain. So I will not write all the technical hypotheses on V that is needed here, but if you have some assumptions on the step size, then you ensure that your Markov chain will converge in distribution to the proper distribution pi theta. Okay, so hopefully I will be able to show you. So many of you probably know that very well, but I would like to show you what you may expect from a Langevin algorithm on a GMM distribution. So here, I've took a step size which is quite small. So as you can see, you will visit some mode of the GMM, but with this integration time, the step size is too small to jump from one mode to another. So it would be consistent. So if you wait sufficiently long, it would actually jump from one mode to the other, but you have to wait sufficiently. In contrast, if I take the initial gamma larger, I hope it will work with this value, you are able to jump from one mode to the other more quickly, okay? But you still have to make your gamma tends to 0 if you want to target the good distribution. Okay, so that was the interlude. Going back to some equations. And so the algorithm that our colleagues came up with tries to use a Langevin algorithm to approximate the gradient of the likelihood that we've written in the first part. So they called it stochastic optimization with unadjusted Langevin because at each step you estimate your gradient with a Langevin which is stopped after mn steps of Langevin, right? So you take mn steps of the discrete Langevin here for the current parameter theta n. This allows you to estimate your gradient with a finite sum. You take a gradient descent step on the theta n. Then you project back onto some closed convex set of parameters. And you initialize your Markov chain at the next iteration with a warm start. Okay, so okay, I will comment on that later. So the algorithm is quite easy to write, and as soon as you can compute your features, like for microcanonical synthesis, you can apply that. And it applies in a continuous framework, which is much more flexible than the Gibbs sampling algorithm that was proposed by Zhu and Mumford in 1998. Right, and here is the theorem that they were able to show. So one interesting feature here is that the function that we wish to minimize is actually convex C1 and with Lipschitz gradient on a compact of parameters theta. Okay, so here we have all these hypotheses which are reasonable to use in our framework. So in particular, our regularization J and the statistics are assumed to be differentiable with Lipschitz gradient. And also we have a kind of control of the tail of the distribution. So here in our function v, I would recall that there is one term which is linked to the statistics f, and one term which is linked to the regularization. And when we use sublinear statistics, morally, this will be the term with the regularization that will dominate. Okay? And so we'll have at least quadratic growth outside the bowl, so at infinity. So this hypothesis will be satisfied. And you also need, so as in Gerson's talk, some hypothesis on the step sizes and the number of Langevin steps. And again, as Gerson said, you have to make a compromise with the number of Langevin steps that you make and the decreasing of gamma n. So yeah, now you can take a picture of this, but I hope I didn't make any error in this side. You would tell me Anna afterwards, right? And I would tell the room tomorrow. Okay, so with this hypothesis, you can actually show that the estimation procedure goes to one minimum of minus log likelihood. And an interesting thing here is that the statistics may not be convex. So it would be okay to use that for differentiable neural networks. Okay. One intriguing thing is that there is a connection with the microcanonical sampling. So I will try to explain that here. If you take a Gaussian regularization, as we said, and you write the Langevin equation here, so you have the gradient of the features f applied to the current parameter theta n, the parameters linked to the regularization, the term linked to the regularization, and the update of theta. But now if you take this set of parameters, which do not fall in the hypothesis of the theorem, and if you remove the noise component completely, then you fall back on this equation. So it's deterministic because there is no noise component anymore, so it's not a Markov chain. It's an initialization and then some deterministic sequence, iterative sequence. But here, you may see that it looks like a gradient descent on the square distance between the feature of the synthesis and the original image, with a kind of C0 sequence here, which is a bit intriguing. So it looks like the gradient descent for the microcanonical sampling that Bruno and Mala use, but with a kind of summation of average here. Okay, so now, so you can relax. We will see only pictures in the last section. So here is the experimental setup that we used. Here the statistics are computed in a given neural network, so VGG 19. Here are the layers that we used for this experiment. So again, the neural network is pre-learned, right? So we will not move the weights of the neural networks. It's completely fixed. And now here are the layers that we used. I guess the precise choice of the layers does not import much, provided that you use some layers in the shallow part and some layers in the deep part to get some structures at various scales. So we took these values of the steps and Mn equal 1. So if you followed very precisely the theorem that I wrote, you may have noticed that Mn equal 1 does not fit the hypothesis. However, they have been working very much to make a variant of the theorem which adapts to this case. And I can say, I think I can say that it's actually true, right? Provided that you use the proper gradient steps gamma n and delta n. Right. The only thing that does not really fit the theorem is that we do not put a projection on a compact set of parameters. But actually, in the experiments, we observe the weight theta to stabilize. Okay, an important thing for imaging is that if you do just the Langevin algorithm with the gradient procedure on the theta, the color distribution is not properly respected, which is a bit weird. I'm not a fan at all of this trick, but in the result that I've shown you, that I will show you, we reimpose the color distribution afterwards, right? So we could probably work on a better way to impose these statistical things also. So here are some results. Like 5 minutes, I guess, to show. Okay. So that would be okay. So here, on some unstructured textures, the result is nearly perfect. There is some small color drifts in the small scales. And as you can see, you have truly derived from the Gaussian initialization. I've not precised that, but we use for initializing the Markov chain a Gaussian random field with a proper second-order statistic. That is really important, and we will see that in the experiment. Okay, so now with a more complex texture, here is what we can hope. As you can see, after many iterations of the SOUL algorithm, there are some structures which are indeed reimposed. And now you can see how they are imposed along the algorithm. So the first iterations are very important to set up some local structure. Afterward, it cleans the image a little bit. But in the end, you don't move very much, right? Between 19 and 1,000 and 2,000, there are some small changes. Of course, there will still be some changes because there is a random Gaussian noise which is added in all the Langevin step, but the step size decreases. So the added noise component will be smaller and smaller. So, and yeah, actually, an interesting thing to show is to compare to the Gaussian initialization. And so the grid structure that you see in the image, it's already present in the Gaussian initialization, right? So I would have been very, very happy to show you some video where you see the texture synthesize and the structures move from one thing to another, meaning there is a spatial mixing. But the truth is, the Markov chain that we use here has a quite long mixing time. And you would have to wait probably much longer to see things move spatially. OK, so here, as I said, one thing that we wanted to do is to improve the method by Lou and colleagues. So here, it's the comparison on the images that were shown by Lou and colleagues. So as you can see, we better preserve the structure of the textures. And in particular, we don't have the scale problem that they experimented. So that's a good thing. Now, if you use very complex textures, so this texture is actually complex because it's very large. Okay, so there are deterministic stacking of objects, which is quite difficult to capture with some statistics. So here is a close-up view of what happens. And as you can see, we have somehow reimposed a bit of structure, but we cannot capture the deterministic way of stacking candies here. And if you compare with the Gaussian initialization, again, you have some yellow, some green stains in the Gaussian synthesis, which have not truly moved, actually, after 5,000 iterations of this procedure. OK, so now comparing to other state-of-the-art algorithm for texture synthesis. So here is the method by Gattis and colleagues, which is probably the best in terms of visual quality. Here is actually another method that we proposed using a semi-discrete optimal transport. So here is Lou and colleagues with a smaller resolution. And here is the result obtained with generative adversarial networks. So as you can see, here, the result of the algorithm we proposed is a bit less convincing, and because, I think it's because the structure here are maybe a bit too large to be captured by the statistics of the neural network. Yeah, one thing I wanted to tell you is that if we are working in a kind of multi-scale trick to improve mixing. So we would like to differentiate in the procedures the very large scales and the small scales to have some more mixing in the larger scales of the texture so that large things move quicker. And so in the last results I have shown, so this one, starting from that, we use a kind of multi-scale trick to improve convergence. Right. So yeah, here you can see, you could understand that GAN is virtually perfect for such texture. Actually, this is not always the case. So for more stochastic-like textures, GAN may actually fail very much. Whereas Gattis is always a bit stable and nearly the best. And also, we get a quite good result here. OK, maybe I will jump to the conclusion. So what interested me very much in this Langevin-based methodology is that it is much more flexible than the original version of the frame algorithm proposed by Zhu, Wu, and Mumford. So you can use it as soon as you can differentiate the features that you use. We have been able to set up a framework where we have a provably convergent sampling and estimation procedure. And so a warm thank to our colleagues to have helped us with that. And we have seen that we are able to synthesize quite convincingly textures using VGG features, right? And one thing is that we have only about 2,500 parameters in this neural network, once you have some spatially. So it's quite a few parameters when you compare, for example, to the method by Gattis and colleagues, which has hundreds of thousands of parameters in general. But of course, the mixing time seems to be quite large. Now, one thing that interests me much is to try to include some other statistics in this framework. So we would have to do many comparisons to see which one are the best perceptually. Probably the neural networks may not be the best from a perceptual point of view, for example, compared to the statistics proposed by Portier and Simoncelli. And there are also interesting connections between micro and macro model, for example, in the work by Stéphane Mala and Joan Bruno. Okay, so I will stop here, and your questions are very welcome. Thank you very much.
Thanks very much. Yes.
Thank you very much. I really learned a lot about this topic. Thank you.
Thank you.
I was wondering what happened if you didn't let the step size of your Langevin algorithm go to 0? You allowed a bit of bias. Have you ever done experiments like that to see if you do jump from one mode to the other and you change the texture?
Actually, I guess that in the original paper by Lou and colleagues, the step size is actually constant. So it's already provided some synthesis results which are quite convincing in that framework. I guess it would probably work as soon as you take a very small value at the beginning. Otherwise, it may go to crazy stuff. But yeah, as soon as it's quite, you confirm? Yeah, that's it. As soon as you take it constant but sufficiently small, the sampling error is not so large.
Okay, any other question? Yeah, go ahead.
So I'm wondering about the influence of the mu relative distribution that you use. So in particular, you use Gaussian, so it means it will have a support everywhere, which is a bit counterintuitive with respect to the image we have of a very sparse distribution in high dimensions. So can we change it, or can we?
You would like to take the reference measure, which is a uniform distribution over images, or?
No, but the problem is, I think as soon as you start using a relative entropy, you have to define a base distribution, and this poses a problem because we don't really know what is the support of the natural images. So it's like a bit like a chicken and egg problem. So I don't know if there is a way to circumvent for this, like. But I guess it's too difficult.
In my opinion, the reference distribution might not. It's important for the theoretical results for now, and to define properly the entropy, but it might not be so important. For example, if you think of the Gaussian model, once you fix your reference distribution, you have a set of parameters that would satisfy the constraints in expectation. So the correlation, the covariance constraint, and the expectation constraint. So changing the reference measure, right? It would give you another set of parameters for satisfying these constraints, but the Gaussian distribution in the end would be the same. So the solution that we use in the end, actually for the Gaussian case, it does not depend on the reference measure.
I know, but it will depend on its support. I understand that it doesn't depend on the reference measure, but it depends on its support. So for instance, you cannot reach a compactly supported distribution with a Gaussian. Okay, it's just a comment.
Yeah,
I have no answer. I think it's a very difficult. I think there is probably no answer.
But probably that we can do many things else.
Okay, Alain. It's gonna be the last question.
This one is scary.
Okay, it's a very naive question. I just wonder if there is really a way to sample the microcanonical set, because I think it's just about finding a point on this manifold. You know, when you constrain to, you want the statistic to be exactly this. Does it exist any way to really sample
your questions
this?
are not really naive, you know that, right?
No,
they are never really naive. If the set of minima of the associated functional is compact or finite, then you have a uniform distribution of the set of minima. Right, so now sampling uniformly, so if you don't know, if you don't have a precise procedure to actually compute exactly those minima, finding the uniform distribution over this minimum is not so easy. So if you think of like a two-mode functional and you think of a gradient descent procedure to sample the maximum, so your uniform distribution on those two minimum, it will highly depend on the initialization of your algorithm. I agree with that.
Then sampling would be just like changing the initial condition. Each time you pick up a random noise,
Right.
Yeah, sure.
When we talk about when we talk of microcanonical sampling, the sampling part is just in the initialization of the algorithm. The rest is deterministic. Okay, so it's a bit weak vision of sampling, right? It's not a Markov chain. It is, but it is a deterministic one. So it's not.
Anyway, so let's leave the discussion to
yeah.
to
Thank
break.
you for questions.
Okay, thanks very much, Arthur.